going to look at a specific family of functions, f of x equal 1 over x to the p. They're going to be really important when we start studying infinite series in the next chapter. So I want to find out for what values of p will this integral from 1 to infinity converge. Okay? I'm going to look at two cases. I'm going to look at when p is equal to 1, and then I'm going to look at when p is not equal to 1. Okay. Now the reason is because when I'm integrating that, if p is equal to 1, I'm going to have the integral from 1 to infinity of 1 over x to the 1. Okay? Using our definition of an improper integral, this is just going to be the limit from 1 to b, as b goes to infinity, of 1 over x. And now to integrate 1 over x, I know that that's just going to be the natural log of the absolute value of x. So this is the limit as b goes to infinity of the natural log of x. And I want to evaluate that from 1 to b. Now that's why I split it up from p equal 1 and p not 1, because that allows me to integrate the 1 over x or the 1 over x to the p by either the power rule or the log rule, because remember it's got that one case, the power rule, it's x to the minus n dx. It depends on whether the n is 1 or not. So this will be equal to x to the n minus 1 plus 1 over minus n plus 1 as long as the n is not 1. Okay, so finishing this problem up, I'm going to now evaluate from 1 to b, so this will be the limit. Natural log of b minus natural log of 1. Natural log of 1, we know, is just going to be 0. Remember our log function. Natural log of b. Now let's look at the graph of the log function, just to remind you. The log function has a vertical asymptote, which is the y-axis, and it passes through where the x is equal to 1. And that's where we get that point is 1 comma 0. And so I'm looking at y equal natural log of x. So that's why I know natural log of 1 is 0, because that's the y value associated with that point on the graph. So now what I want to find out, though, is if this b is getting closer and closer to infinity, and b is just the argument of this log function, so that means as the x is getting closer to infinity, what's happening to the natural log? And you can see in the graph that it is rising. It's rising very slowly here, but it is going to continue to rise. So that limit then is going to be infinity. So this will be infinity. So that means this integral actually diverges. So if the p is equal to 1, the integral of 1 over x dx will diverge on that interval from 1 to infinity. So that means that if we were trying to get that area from 1 to infinity, the area is just going to continue to grow and grow. And you can see that because that function's rising as x gets closer to infinity. Okay, so now let's look at p not 1. If p is not 1, I now have the integral of 1 over x to the p, which I'm going to rewrite it as x to the minus p. And that, again, is just going to be the limit as b goes to infinity of the integral from 1 to b, x to the minus p. Okay, now using the power rule, since the p is not equal to 1, the power rule says that this integral will be x to the minus p plus 1 over minus p plus 1. Okay? And we're going to evaluate that from 1 to b. Okay, so now I need to plug in b and 1 for my x. So this is going to be the limit of b to the minus p plus 1 over minus p plus 1, and then minus what I get when I plug in x equal 1. So I'm going to have 1 to the minus p plus 1 over minus p plus 1. And this is as b goes to infinity. Okay. Now I notice I have that 1 over minus p plus 1, it's the denominator in both of those two terms. I'm going to go ahead and just pull that out in front. So this is going to be the same thing as minus 1 over, not sure why I'm put that minus there, 1 over minus p plus 1 times the limit, I can just put the, pull it all the way out of the limit, b to the minus p plus 1 minus, now let's look at this next. 1 to a power, p is not 1, okay? P is some real number. I have 1 to some real number power. It doesn't matter whether that exponent's positive or negative. 1 to some real number power is always going to be 1. So this thing is 1. So I'm just going to go ahead and replace that. Okay, so I'll pull the denominator out of both of these, and then I just have that numerator left. Okay, so now what I need to do to figure out this limit is I need to understand the size of the b. I don't know whether the exponent here is positive or negative. It depends on the size of p. So what I'm going to do here is I'm going to look at two cases. I'm going to look at the case where p is bigger than 1, and then I'm going to look at the case where p is smaller than 1. That's going to allow me to figure out what this value is going to be. Okay, in the front, I still have 1 over negative p plus 1. So this will be 1 over negative p plus 1 times, okay, now if p is bigger than 1, what do I know about minus p plus 1? Okay, well, I can find that out pretty easily if I take this p greater than 1. I'm going to subtract p from both sides. That means I'll have 0 greater than 1 minus p, which is the exponent, minus p plus 1. That means that that exponent is negative. If the exponent's negative, I'm going to rewrite this now so that the exponent's positive, because then it's easier for me to evaluate that limit. So I'm going to rewrite this as 1 over b. Now I need to change the sign of the exponent, so now it's going to be p minus 1. And my b now is going toward infinity. Okay, b is getting larger and larger. I know p minus 1 now. Remember that 1 minus p was negative. That means that if I moved everything to the left side, p minus 1 would be positive. So that means this exponent's now positive. And b is a big positive number. So if that exponent's positive, that means the denominator is growing as the b goes to infinity, which means 1 over that is going to 0. So that means that this limit would be 0. Forget this out here in front. 1 over minus p plus 1 times 0 minus 1, which then comes out, let's see, I'm going to take this negative 1, I'm going to go ahead and distribute that in the denominator, and this comes out to be 1 over p minus 1. So p is some real number. That means that if p is bigger than 1, that limit, that integral converges to 1 over p minus 1. So this was the case when the p was greater than 1. This was that integral value. So the integral from 1 to infinity of 1 over x to the p will be 1 over p minus 1 if the p is bigger than 1. Okay, now let's look at the other case. If p is less than 1, I've still got this expression, 1 over minus p plus 1. I've got that limit. Okay, now I need to figure out right here again, what do I know about minus p plus 1? Well, if p is less than 1, that means if I subtract p from both sides, I'm going to have 0 is less than minus p plus 1. What that tells me then is that minus p plus 1 is positive. It's greater than 0. That means this is a positive exponent. Okay, so I'm just going to leave it in the numerator. So I've got b to the minus p plus 1 where this is positive. And then I've got my minus 1. So now as b is getting closer and closer to infinity, I've got this number growing with a positive exponent on it, which means that that's going toward infinity. So this part would go approach infinity. And so that means that this limit is going to be infinity, and that means that this integral from 1 to infinity, 1 over x to the p, diverges. It approaches infinity if the p is actually less than 1. Now what happened when the p was equal to 1? When the p was equal to 1, we also got that it was infinity. So that means then that when p is less than or equal to 1, this integral diverges. So this is the results that I want you to know, and we will use these extensively in Chapter 9. The integral of 1 over x to the p converges when the p is bigger than 1. And we know what it converges to. It's 1 over p minus 1. It will diverge, though, when the p is less than or equal to 1. So that means that area will continue to grow if the p is less than or equal to 1. Whereas if the p were bigger than 1, that area is going to taper off, and we can actually find the finite value for that area. Okay, let me show you these graphs. This is looking at the different values of the p here. I'm looking at p equal to 1 right here. It's the one right in the middle. If the p is equal to 1, that's the function 1 over x to the 1 power. That one we got diverged, which meant if you tried to get that area under the function from here all the way out, that function's not tapering off enough, so that area is continuing to grow as x gets larger and larger. Whereas if we picked p equal to 1/2, this one's one where this is p's 1/2, so that's 1 over x to the 1/2, or the square root of x. That one is where the p is less than 1. And you can see there that it's not tapering off either. It's actually larger than, further above the x-axis than 1 over x was. This one also will diverge. Okay. And this one, the integral diverged. But if we look at 1 over x squared, that bigger power of the denominator, the 1 over x squared, is causing that function to get closer and closer to that x-axis faster. So that if we're trying to find that infinite area, it's going to taper off, and we'll actually be able to find that integral. So that actually means we found here that depending on the p, we know what the integral actually is. Integral of 1 over x squared. The p here is called a p series. When we're talking about series, it'll be a p series. When p is equal to 2, this is going to be 1 over 2 minus 1, which is 1. And that's going to be that infinite area from 1 to infinity. So we actually can find, if I want the integral of 1 over x to the 3rd, this one will converge because the p is bigger than 1, and it's going to actually converge to 1 over 3 minus 1. So as long as the p is bigger than 1, this integral converges, and it converges to 1 over the p minus 1.